Hi, everyone. Can I ask you guys to stop talking? And we're going to start by taking any questions from the homework assignment. So if you have a question or questions from the homeworks, now is the time. Yes, Colette? Looking at 34. It wants us to find the parameterization for the line segment with the indicated endpoints. Okay. So I'm going to start by writing my vector equation for a line. So vector v I can just do as the first vector minus the second vector. And then for r naught, I can use either vector. I'll just choose to use the first one. And so what this gives me now is my parameterization. The only question now here is the interval for this parametric function. So clearly when t equals 0, r is going to give me the point 2, -4, which is one of my two endpoints. So I know that my interval is going to include that point 0, either the start or the end. I'm not sure which. So then I'm going to check t equals 1. When I do that, r would give me -2, -9. This is not the other endpoint. So let's try -1. When I do that, I get +6, and then +1, which is my other endpoint. So my interval should be from -1 to 0. Well, when t is -1, I get one of my endpoints. When t is 0, I get the other endpoint. So if you write your parametric function from the vector equation, you're always going to have a unit interval for the parameter. It'll either be from 0 to 1 or -1 to 0. So you just need to kind of check which one of those two it is by plugging 1 or -1 in for t and see if you get the other endpoint that you need. Does that make sense, Colette? Okay. Anyone else with questions from this assignment? Yeah, Colette? 42. So this says a ball is thrown straight up in the air from an initial height of 5 feet. With an initial velocity of 80 feet per second. Write an equation to model the height y in feet of the ball during as a function of time t in seconds. Well, that's not really much of a sentence, but okay. I get what we're asking for. Since this is we're going straight up and down, I can use the first version of these equations. That specifically is s of t is equal to 1/2 t squared, or I'm sorry, negative 16 t squared plus v naught t plus s naught. So it says to use y for the height, and my initial velocity is 80, and my initial height is 5. So there's my y equals equation. It says how high is the ball after t second, or after 3 seconds. So there I'm just going to be plugging 3 in for t. Whatever that comes out to be. Let's check real quick. Should be 101 feet. And then part C asks for what is the maximum height of the ball and how many seconds does it take to reach its maximum height. So remember, for a quadratic in the form ax squared plus bx plus c, which is what our height equation is, right? That the highest or lowest point is going to happen at the vertex. And to find the vertex, I can do negative b over 2a, and then I'll plug in negative b over 2a into my function to get the y coordinate. So for our case, that time where we reach our maximum height is going to be negative 80 over 2 times negative 16. So that reduces down to, let's see, that's 8 times 10, and that's 8 times 2 times 2, so I end up with 2.5, I think. And to get the maximum height then, what I'll do is I'll plug 2.5 in. And when I do that, I get like 105, I think. Okay with that, Colette? Okay. All right. So let's move on here and start talking about the next section. So in this section, we're going to introduce the polar coordinate system. And I'm going to abbreviate this as PCS, just because it's a little bit more convenient than writing all those letters, because I'm going to have to say that a bunch of times. What I'm passing out right now is just a printout of a polar axis. So if you want to use this to kind of take some notes to work on some of the homeworks with or whatever. This file is also available to download if you go and look at the class page and look at the course materials. You can find a blank version of this also if you end up wanting some more of them or whatever, but I think it usually makes taking some notes a little bit easier when I put this up here and start talking about parts of it if you have one of your own. Because sketching this on your own is, yeah, I mean, it's not really realistic expectation, right? All right. So up into this point, when we've done any graphing, we've always graphed on the Cartesian coordinate system, graphed x's and y's, right? Even when we dealt with these parametric functions in the last couple of sections, when we graphed them, we're still graphing x's and y's, right? The graphing part of it didn't change. Now, for parametrics, we had to generate our x's and y's separately by choosing values for t, but whatever. The plotting of the points didn't change any. This is not true when we start talking about polar functions. We're going to use a completely different set of axes to graph things on when dealing with polar functions. That new set of axes is the polar coordinate system. You can see in the sheet that I just passed out to you that it looks decidedly different than necessarily the xy axis. So the plan for today is really just going to be talking about how we graph things, like how we plot points, specifically really just talking about plotting points, and then converting back and forth between Cartesian and polar coordinates. Okay, so that's kind of the plan today. So we'll start with just the definition. Okay. So a point in the polar coordinate system is defined by the general form r comma theta, where r is the distance from the point to the origin, and theta is the standard form angle whose terminal side intersects that point. What does this remind you of, this description here? Should immediately be reminded of something else that we've talked about earlier this semester from this description. What? Yeah, this should remind you of a two-dimensional vector, right? One description we had for a vector was a magnitude and a direction, basically a length and an angle. That's exactly what we're describing here. R is a length, theta is an angle. It's very similar to the idea of a two-dimensional vector. So let's talk here a little bit about this polar axis that we've just given you guys. Shoot. Let's put one up here that I can draw on. Okay. So if we take a look at our polar axes, hopefully you guys notice that we still have a pair of perpendicular axes that look similar to the XY axis, what we're comfortable with, right? Okay. But we have a bunch of other straight lines here also kind of going all over the place. Each one of these wedges is 30 degrees. So you can count around as such. Everybody okay with that? Or if you prefer to have them in radians, (30 degrees is pi over 6. And obviously these fractions you would reduce, but I think for note-taking purposes it's probably easier if I write the non-reduced fraction there so you can see that all we're doing is really counting by sixths. Is everybody okay there? Okay, so that's what these other diagonal lines are doing. It's just kind of giving you some angle measures. And then the other piece of this is that we have all these concentric circles, right? So this first circle is a unit circle. Its radius is 1. The next circle out is a 2-unit circle. Its radius is 2. And I can kind of continue working my way outward. You know, the next circle is a 3-unit circle. Its radius is 3. And I could keep going. Each circle is another 1 radius larger than the previous. Is everybody okay with how I'm reading this axis? Okay. So I'm going to erase all this stuff here, and we're going to practice plotting some points now that we understand kind of how to read this thing. So the first point we're going to plot is 3, 120 degrees. So the way that I like to do this is I first like to locate my 120 degree angle. So if I count along the wedges, I have 0 degrees, 30 degrees, 60, 90, 120. So the line that I'm interested in, the terminal side for that 120 degree angle, is that right there. Everybody okay with that idea? Okay, so my point is going to lie on that highlighted yellow line somewhere. Where is it going to be? Well, it's 3 units down that line. So each circle we intersect, we remember, is 1 radius longer than the previous. So this is 1, 2, 3. So the only thing you really need to draw on your sheet of paper is the point. I drew all this extra stuff so you could kind of see what I was doing to graph this. You don't need to highlight anything. You don't need to draw any lines. You don't need to do any of those sorts of things. Just have the point in the proper location. I just wrote down some stuff so you could see how I was doing that. Is everybody okay there? Let's do another. God bless you. God bless you. Okay. So the next point I'm going to plot is the point -2 pi over 3. So remind me again, pi over 3 is basically 2/6 pi. Everybody agree with that? So the terminal side of my angle is this one right here. Everybody good with that? Okay. But this time I'm going to go -2 on this units along this line. So which way am I really going? I'm going down here, right? So 1, 2 would be down here. Is everybody okay there? Okay. And let's do one more. So let's do -1, -100 degrees. So remind me again, how do I deal with a negative angle? Yeah, I'm going the other direction, so I'm going clockwise instead of counterclockwise. So 30, 60, 90. So -100 or -100 degrees is going to be like 1/3 of a wedge, right? So 90 degrees, and then I need 10 degrees more. 10 degrees more is going to be like 1/3 of that wedge. Oops, I don't want to draw that much of it. So maybe like there, right? That's a reasonable estimate. You're just going to kind of have to eyeball it, but you want about 1/3 of that wedge. Everybody's okay with that? So that's the terminal side for my -100 degrees. But how far am I going down that terminal side? I'm going -1 units. So really the side of it that I'm going to work on is over here. So this point is really in the first quadrant. Everybody feel okay about how we're graphing things here? Okay. So it's not too hard, but it's decidedly very different than the kind of graphing that we're used to, right? Especially when we like flip the direction over which we're graphing on, right? So here's a question for you. Let's say we're looking at the point -2 pi over 3. So let's say we're looking at this point here. Is that the only way that I could represent a point in that location? No. Okay. What else could I do? So what's another point that looks different but is still describing the same location? 2, 240 degrees. Okay. Let's write that in radians, though. Is that okay? Okay. So that would be, I think, 4 pi over 3. I think is what that is. Okay. So that's one way to do it. So everybody's okay with that. What's another way? Can we do it without changing the sign on the 2? Does anybody think of a way to get a different ordered pair that's still describing the same location where it still starts -2? -260. Oh, -2 comma 60? Well, I mean, that's still pi over 3 and 60 are still the same angle there, right? So I'm looking for an angle that's not. What? Yeah, so if we add 360, so that would be like 7 pi over 3. That'll do also. So I think that we have a special name for angles like pi over 3 and 7 pi over 3. They are called coterminal. Yup. So that's certainly one way of finding them. What is the pattern to find other points like Miguel found?
Flip the sign.
And then what?
Go to the other side.
So when we say go to the other side, you're describing, so this was the terminal side that we were working with before, right?
Yeah.
And we want the angle that Miguel described was this terminal side. So how do we change the angle? To go from here to here.
Just make it too positive when you do the line that's down.
So let's describe it like symbolically rather than geometrically. What are we adding to that angle or subtracting to that? 180, good. Good. Or pi, same difference, yes. So let's formalize this then, these observations. So given a point P in the polar coordinate system, any other point that coincides with P must be of the form. Do we know what coincides means? Okay. What do you think based on what we've just been talking about? It's the same location, right? So points that coincide have the same location. Even if they're different ordered pair, they share the same location. So the first option is our coterminal situation that Mark described, right? Where we're just going to add a multiple of 2 pi to the angle measure. The second ordered pair there is the situation Miguel described. We're going to change the sign on the R and then add 180 degrees or pi to the angle. And then we can also choose anything coterminal to that angle as well, right? Everybody's okay with that description? We could also describe this situation using degrees as well. Yes. Yes. Okay. All right. Let's do a little example here. So let's find all the polar coordinate points that coincide with the point 8, 5 pi over 6. So which version of the above definition are we going to be using? The radian or degree one? The radian one, since our point was given in radians. So let's do this point first, or that set of points first. So here we have 8, 5 pi over 6 plus 2 pi n. And then let's do this set of points second. So here we're going to have negative 8, 5 pi over 6 plus pi plus 2 pi n. And we can add 5 pi over 6 and pi together, right? That gives me 11 pi over 6 plus 2 pi n. Again, where n is just some integer. And that's my answer. That's the formula above from the definition. The yellow is in red, blue is in blue. Need to have both of them because it wants all the points that coincide, so you have to have both sets. Okay? I just made a common denominator and added the fractions. Is that okay? It is.
Let's go.
All right. So the last topic that I want to talk about today is converting between polar coordinates and Cartesian coordinates. Just as a vocabulary thing, sometimes the Cartesian coordinate system is also referred to as rectangular coordinates because the graph in XY, basically you're drawing a rectangle. So those two terms could be used interchangeably, and I think we do that in the note or in the typed out notes, and it might be that way in the homework sets too. So let's start with a definition. Okay. So, if point P has the polar coordinates r theta and the rectangular coordinates x, y, then the following four relationships hold. X is equal to r cosine theta. Y is equal to r sine theta. R squared is equal to x squared plus y squared. And tangent theta is equal to y over x. All of these are just natural consequences of what we know about circles and triangles. So let's do an example. Yeah.
At the end of the definition, does that say but or is that in that?
Then.
Then?
Yeah. Because it's if-thens. So let's convert the point -3, 148 degrees into rectangular coordinates. So from the above definition, which relationships are going to be useful to me? The first two. Why the first two? Well, we're looking for rectangular coordinates, so we need an x and we need a y, and then we know the r and we know the theta, so we have everything we need with those first two. So x is going to be -3 times cosine 148, and y will be -3 sine 148. And if I type this into my calculator, I get positive 2.54 and negative 1.59. Again, I rounded those to 2 decimal places there. For you, my good man.
All right.
Tuck your shirt in. So that's pretty easy, right? Let's go the other direction then. So let's take a rectangular coordinate, -3, 2, and rewrite that as a polar coordinate. So if I go back up to that previous set of definitions, which relationships are going to be valuable to us? Yeah, the other two, right? So R is easy to get right away. So R is going to be the plus or minus square root of 13. My suggestion to you is just always choose to use the positive one. Remember, if you're describing a point in the polar system, the R could be positive or negative, and you can still get to the same location. So it's usually just easier to think about the R being positive and not have to worry about like flipping things. But there's certainly answers. You could use a negative R and be fine. We're just going to choose to do the positive because it makes life a little bit less complicated. Everybody okay there? Okay. Now for the second relationship, we have that tan theta is equal to y over x. But what's going to be the problem here as we try to solve for theta? Okay, so we have to take the inverse of tangent. And there's a negative, so what? What's the range for tangent inverse? It's negative 90 to positive 90. If I look at the angle here, if I were to plot 3 pi over 2, is that angle between the two that we specified there? No. So we're going to have to do some adjustment here. Okay? So what I'm going to do is I'm going to solve for a different angle called alpha by doing the tangent inverse of the absolute value of 2 over negative 3. So we're looking for this angle theta. What we're finding here is this angle alpha. What's the relationship between theta and alpha? Just look at the picture, man. Yeah, they're supplementary, right? They're going to add up to give you 180 degrees. So which one are we actually interested in finding? Well, we need a theta for the polar coordinate. So that's just going to be 180 minus alpha then, right? So if I type in then 180 minus the tan inverse of 2/3, that comes out to be 146.31-ish, because this was 33.69-ish. Okay. So we're going to stop here. For next time, I'd like you guys to do 49 to 62.